This is our second lecture under Boolean Algebra. Okay. Last class we discussed few theorems in Boolean Algebra and postulates. Then at last we discussed logic gates and their properties. Right. Okay. So shall I continue? So let me recap what we have learned in the last class. Okay. We have learned a few theorems in Boolean Algebra. One important theorem was duality theorem or duality principle. Okay, duality theorem or duality principle, duality theorem, right? And we said that to convert an expression into its dual expression, right? We should not change the variables. That implies no change of variables. Okay, and if you're having or sign, we should replace or with a and sign. Okay, and sign. Similarly, and sign with a or sign. Okay, or sign. And if you are having logic constants, let us say 0 and a 1, right? We should replace 0 with the logic 1. If you are having 1 in the expression, we should replace it with the zeros. Okay. For example, if you are given that a plus b dot a plus c equal to 1. Okay, its dual expression is very simple. Variables no change, or sign to and sign, no change for variable. This is and sign that I should change to or sign, no change for variable, or sign to and sign, no change for variable, no change for equality. Right hand side we are having a logic 1, we should replace it with a logic 0. Okay, also we have learned a few theorems, right? One important theorem was a plus b dot a plus c equals a plus bc. Okay, that is called a distributive law. So a plus bc, right? And we also learned that a plus x dot with a plus y is nothing but a plus xy, right? Right. A is the first term, right? That first term or with the product of two other terms, right? Suppose we are having expression a plus b dot with a plus c. We should simplify it as a plus b dot c. Okay, a plus b c. Right. That was another theorem we have learned in the last class. Right. Okay. Also, we have discussed that the identity law, that is, if we are taking product with the same variables, the result will be same variable itself, x dot, etc. will be x itself. Similarly, if you are taking the or operation between the same variables, etc., the result will be x itself. And we discussed one more important identity, that is a plus a complement b was equal to a or b. Correct? Correct. A plus a bar b is equal to a or b. Right? A plus a bar y equal to a plus y. Right? Or w plus w bar x is nothing but w or x. Right? So a plus a bar b is equal to a plus b. Correct? Also, we have learned one more theorem, important theorem, that was De Morgan's theorem. Right? De Morgan's theorem was very simple. It has two statements. The statement was x plus y plus z plus etc. equal to product of their individual complements, right? So x bar dot y bar dot z bar. right? And the second statement was x dot y dot z dot etc. The whole complement. Complement of a product is equal to sum of individual complements, right? All these you can expect one word questions, okay, right? Which one of the following is Boolean, sorry, which one of the following is a De Morgan's law, right? A, B, C, D, four different options will be there. Okay, so these are two statements in connection with the De Morgan's theorem or De Morgan's law, right? Complement of a sum equal to product of individual complements. Complement of a product is equal to sum of individual complements, right? Okay. Also, we learned in the last class, that the main concept in digital electronics, that was min and max terms. Okay, min terms and max terms. Min and max terms, right? Min and max terms. Sharon asking me to increase the volume. Actually, I think my volume is perfectly all right. What about others? Everybody can hear me properly? Any issues? Please respond. I think my level is clear here, so Sharon can increase the speaker's volume. Okay, right. Okay, so let us continue. The main portion was min and max terms in the yesterday's class. Okay, min and max terms. And you are right now, you are familiar with min and max terms. You can easily identify min and max terms from a truth table. Okay, so the function can be expressed either using min terms or using max terms, right? If you're representing the function using min terms, the representation is called sum of individual product, SOP form, right? Okay. If you are representing the function using max terms, the representation called POS representation, product of individual sum, right? So the min terms are product terms, okay? Min terms are product terms, and that product term should return a logic 1. Similarly, max terms are sum terms, right? And that sum should return a logic 0, right? So if you're having a truth table, to identify the min or max terms of a given function in the truth table, just cross check with the truth table. The column of f is equal to 0 implies that combination is its max term, right? If that particular column is 1, that implies the corresponding combination is its min term. For example, if you're having a two variable system, let us say a and b, right? 0 0 0 1 1 0 1 1, and this is my function f. Its arguments are the inputs a comma p, right? So if it is described like this, let us say 1 1 0 0. So the function can be represented as f of a comma b equal to, using min terms. Which are the min terms? Min terms implies with f equal to 1, right? So these two combinations, 0 0 and 0 1. 0 0 combination implies decimal equivalent is 0, so it's 0. 0 1 implies decimal equivalent is 1, so sigma 0 1. The same function can be also expressed using max terms, right? How to identify max terms? Identify the zeros in the function, right? And the representation of max term, it's a product, right? Product of individual sum. So product is represented by pi. Its arguments are pi of, look at the truth table, this is 0, this is also 0. That implies these two combinations. Decimal equivalent of second last combination is 2, and the last combination decimal equivalent is 3. So this is 2 comma 3. So we can easily identify min and max terms, right? Also, you can directly write the expression by looking at the truth table, right? 0 0 implies 0 implies 0 0 binary. Decimal 1 implies 0 1 binary, right? So this is nothing but a bar dot b bar or with second possibility is a0 b1. Okay, a0 b1, so that is a bar dot b, right? So these are individual products and we are taking the sum, so sum of individual product, and this is my SOP form using Minterms. Similarly, I can also express the function directly using the max terms, right? Max terms are 1 0 and 1 1. And you should recall the max term should be a sum term. That sum should return a 0, right? So a1 b0 implies I should OR with the a complement and b, right? Then only the sum will return a logic 0 because a equal to 1 and b equal to 0. So a complement will be 0, b is anyway 0, 0 or 0 will be 0. And I should take the product with another combination, that is max term 3, 1, 1. Both inputs are 1. That implies I should take a complement of both the variables. A complement will be 0, b complement will be also 0. 0 or with 0 will be 0. So the product will be equal to 0, right? This is corresponding to 1, 1, right? Okay. So while writing the max expressions, you should take care that the variable with the logic 1 should be complemented, right? And the variable with 0 should be repeated as it is. Okay. Whereas in case of your mean term expression, the variables with the logic 0 should be complemented, right? Right. Variable with logic 0 should be complemented, and the variable with the logic 1 should be repeated as such, right? And we identified mean terms of different logic gates also, right, in the last class. Okay. So this is a small recap of what we have learned in the last class, and this will be useful to those students who were absent in the last class. Okay, right. Okay, so let us resume logic gates in today's class. Okay, basic gates were first one was OR gate. Okay, we have learned OR gate, A, B, A or B. Okay, then we have learned AND gate, A, B, A and B. Then we have learned the complement of these two logic gates. They are NOR, right? NOR, A plus B the whole complement, NOR gate, and this was NAND. Okay, NAND, A, B. So A dot B the whole complement. Okay, and the other gate were XOR, right? A, B, and we identified the symbol for XOR operation is like this: XOR B, A XOR B, right? And the complement of XOR will be X NOR, right? And these are dual to each other. Dual of XOR is X NOR, right? Similarly, dual of X NOR is also equal to X OR. Okay, they are dual to each other. And we know that how to take a dual expression. This was A. We wrote it as A. This is B. We will write it as B. And there is a circle, right? And inside the circle, I am having OR sign that should be replaced with a AND sign to get a dual gate of XOR gate. That is X NOR, right? X NOR and XOR. And at last, we have discussed NOT gate also, right? A complement. That is called NOT gate, right? And we have one more logic that is called a buffer that we didn't discuss in yesterday's class. A buffer is nothing but a simple logic that will output same input, okay? Whereas not will produce a complement of input, right? Here, output and input are same in the case of buffer, okay? Buffer. And the property of the buffer is that output will be same as input. And the second property is that output is the delayed version of input, right? So the property of a buffer is nothing but Input will appear at the output as it is, but it's a delayed version. Let us say 1 nanosecond delay. So if you're applying input, the same input will appear at the output after 1 nanosecond. Right? Of course, all logic gates will have a delay, right? That delay is called propagation delay. Propagation delay. Propagation delay. Okay, propagation delay, or it's a time that takes to propagate the input to the output side. Okay, right. If you are applying a proper input, we are expecting some kind of output. There will be a delay. We may not get the same instant. We will not get the output, right? So we should apply the input. We should wait for small time. Then only we will get the output. That delay is called propagation delay. Ideally, if all gates are ideal gates, propagation delay will be 0. But in practical cases, there will be an appropriate propagation delay for different logic gates. And that propagation delay depends on how we are constructing the logic gates, or the technology behind the construction of logic gates will decide the propagation delay. Okay, some logic families will have least propagation delay, some other families will have highest propagation delay, some other families will have moderate propagation delay, right? It's all about the construction of logic gates and their families. Okay, right. So up to this point we have discussed. Buffer was not discussed in the yesterday's class, so that I have included. Then we'll see some more properties of logic gates from which you can expect questions in the examination. Right? Okay. Rajendra Maurya is saying that please speak loudly. I think I'm speaking loudly, and none of others is having issues, I think. Right? Rajendra Maurya can increase the speaker's volume. Okay. At your end. Right. Okay. So let us continue with logic gates. Right. In some questions, you will see that you are given with AND gate, okay, and both of its inputs are tied together, and it is called X input. And they may ask you what is the output Y, right? From the symbol, we understood that the logic gate is which logic gate? AND logic gate, right? AND gate. And the property of AND gate is that it takes the product between its input. Here it is X, here also it is X. So Y will be equal to the product of X and X, that is same as X, right? So an AND gate with its inputs connected together or shorted together will act as, which gate it is? Will act as, output is same as input, correct? Output is same as input. Which gate it is? It is called a buffer, right? It's a buffer, okay? Buffer, right? An AND gate with the inputs connected together act as a buffer, right? So look at OR gate. What happens in the case of OR gate? Here also both inputs are connected together. Let us say X and X. Y will be OR operation between two inputs. Both inputs are X, so X OR with X, and that is same as X itself. So this also act as a buffer, right? Correct. Let us look into the other gate that is called complement of AND, that is NAND gate. Okay, NAND gate. Right, inputs are connected together. What about Y? Look at the gate Y. It's a NAND gate, correct? NAND gate. So the property of the NAND gate is that it takes the product first. Okay, it takes the product, then complements. Correct. So X dot X, the whole complement. X dot X is nothing but X itself. So this is nothing but X complement. Y equal to X complement. Output is the complement of input. Correct? Correct. And that is equivalent to which gate? It acts as a NOT gate. right? A NAND gate, NAND gate with inputs connected together act as a NOT gate. Similarly, if you are looking at NOR gate, NOR gate with inputs connected together, right? Let us say X and X. This is X, this is X. It's a NOR gate, NOR. So Y will be equal to sum of inputs followed by a complement operation, right? So that is nothing but Y equal to X, or X is X itself. So X complement. So this is also equivalent to a NOT gate. Correct? That also may be in the examination question paper. Okay, right? And we have two more gates. Okay, right. Your feedback is contradictory. Venkata is saying to increase the speed, and Chetana is saying that speed is okay. Okay, right. So slightly I will increase the speed of my class. Okay, then let us see. Okay. So let us get into another gate that was XOR and XNOR gates. Okay, XOR gate with the inputs connected together. Okay, let us say X is the input. Here also X will appear. Here also X will appear. Right, and Y expression was, right, A bar B plus A B bar. Correct. Let me call this as A, this as B. Okay, and both equal to X. Right. Okay. So A equal to X, B also equal to X. So this is nothing but X bar dot X, or with X dot X bar, right? And everyone knows this. What is X dot X bar? X dot X complement, X dot X complement and X complement dot X both are equal to zeros. So 0 or 0 will be 0 itself, right? So Y is always equal to 0. Right, that is obvious. Why that is obvious? The property of an XOR gate was, what was the property of an XOR gate? If you are giving same inputs or similar inputs, if inputs are same, then output will be 0, right? Here we are giving X and X, inputs are same, right? If X equal to 0 0 0, X equal to 1 1 1, both cases they are same, so output will be 0. Correct, right? So if inputs are shorted together or connected together, the output of XOR gate will be 0, right? Similarly, if you are going for XNOR gate with inputs connected together, let's say X and X. Let me call this as A input, this is B input, right? And we know that the expression was A complement B complement, that is 0 0, or with A dot B, that is corresponding to 1 1, right? In your gate XNOR operation, the output will be equal to 1 if inputs are same. So here and here inputs are same. All other cases output will be 0. So 0 0 is represented by A bar B bar in SOP form, sum of individual products, right? 1 1 is represented by A dot B, right? So two cases, two terms, right? So here both X and Y are, sorry, A and B are X, okay? So this is nothing but X complement plus X dot X, right? Both A and B are X, right? So X dot X bar will be X bar itself, X dot X will be X itself. So X bar plus X, A bar plus A, X bar plus X will be equal to 1. So this will produce a logic 1, correct? That can be remembered easily by using your common sense, right? Property of XNOR was it produces output if inputs are same. Inputs are same. So we are connecting together, inputs are same. So output will be 1, right? Okay, right. Copied, done? Then please respond. Copied? Yes? If copied, you please type C in the chat box. Okay, right. So let's have some more properties of my logic gates. That is, in your AND gate, I am placing an inverter, okay, or NOT gate before the actual input of my AND gate. Let us say X and Y are the input. Or again, let me write as A and P, and that is easy for me. A and P, right? And you know that the property of AND gate is that it will take the product of its inputs, right? Actually, what are the inputs? A complement will appear here because this is a NOT gate, okay? Output and input of NOT gates are complement to each other. A is applied here, so A bar will be the output. B is applied here, so B bar will be this, okay? So please listen carefully. So that AND gate will produce the product, that is A bar dot B bar, product of its input. Its actual inputs are A bar and B bar, and output will be the product of these two, A bar and B bar. Okay. And if you're recalling your De Morgan's law, it is actually product of complements, right? Product of complements. What was De Morgan's law? It is product of complements, and the product of complements is nothing but complement of a sum, correct? Complement of a sum is equal to product of their individual complements. So this is nothing but A plus B the whole bar. What is that? That is equivalent to which gate it is? A plus B the whole complement. That is NOR gate, correct? NOR gate. Okay? NOR gate. NOR gate. So an AND gate with inputs complemented will act as OR, sorry, NOR gate. There should be a bubble. NOR gate. NOR gate. Correct? And this connection of inverters, we will represent it by a small circle, right? Small bubble. Okay? Small circle or small bubble. Right? That implies an inverter is placed similar to this. Inverter is placed in between the input and actual input of the logic gate. Okay. So this is called a bubbled. This is a bubble. Okay. Bubble. Bubble is corresponding to inverter. So bubble. Right. So this is called a bubbled. Bubbled. Bubbled and gate is equivalent to which gate? Or NOR gate, correct? NOR gate, right? So bubbled and is equivalent to NOR gate. You please keep this in mind. Okay, clear? Equivalent to NOR gate. Okay, this is A or B the complement. Then please listen carefully. We are going to make use of our duality principle here. Okay. Look at the inputs. A is the input, B is the input. I'm taking the dual, right? Variable won't change, right? Then I have a line. Dual of the line will be same line itself, not change. And I have a bubble. Bubble implies a NOT gate. What was the dual of my NOT gate? Dual of a NOT operation. Dual operation of NOT operation. What is that? Yesterday we discussed. Right. Dual of NOT gate is NOT gate itself, right? So it appears as bubble itself, right? Then the third gate is AND gate. What is the dual gate of AND gate? What is that? Dual of AND. AND is nothing but A dot B. What is the dual? A or B, correct? So I'm taking dual of this. I got it as a bubbled OR gate, correct? Bubbled OR gate. And dual of my equivalency, same equivalency, right? Dual of my variable A on the right hand side, here it is A and B itself, right? I had an equivalency here, then I'm taking the dual of that equivalency. Okay. So A and B, what is the dual gate of NOR gate? Look at this. This is a NOR gate. NOR gate is A or B the whole complement. How to take the dual of this? A or with and B with B itself complement we should write as such. Right. So A dot B the whole complement. That is NAND gate. Correct? NAND gate. Okay. NAND gate. Right? So bubbled and is equivalent to NOR, bubbled NOR is equivalent to NAND. You can cross check this. Okay. So this is nothing but a OR gate with a complemented input. So this is A bar plus B bar. As per De Morgan's law, A bar plus B bar is nothing but A dot B, the whole complement. And that is my NAND. Clear? You can expect a question based on this. Bubbled AND gate is equivalent to NOR. What about bubbled OR gate? Bubbled OR is equivalent to which gate? NAND. Okay. Bubbled OR is equivalent to NAND gate. Okay. Clear these two equalities? Then please respond so that I can move comfortably to next topic. Then yes or no? Is that clear? Any queries, any doubts, any clarifications required? Right? Bubbled AND is equivalent to NOR, bubbled OR is equivalent to NAND. Right? And you're having some doubts in your mind. What about a bubbled NAND, bubbled XOR, bubbled XNOR, okay, bubbled NOR, okay? All that we'll take up. Okay. So shall I move to next slide? Right. If you're having any doubts, you can ask in the class. Okay. We are spending 2 hours on this, right? Everyone will be busy after the class and before the class. So anyway, we are sitting in the class. So in the class, let us learn it. Okay. If you are not able to learn it properly, please place it in the chat box so that I can repeat. Okay. Otherwise, if you're comfortable, just type CLR for clear so that I can confidently move to next topic. Right. So I'm moving to next slide. Okay. Next slide, we'll have some questions. Okay. Questions, right? Bubbled, bubbled, bubbled. NAND gate is equivalent to NAND is equivalent to 4 options. Bubbled NAND, NOR, AND, or NAND. Bubbled NAND is equivalent to, right? Very simple. NAND is nothing but A dot B all complement. Bubbled NAND implies A will be replaced with A bar, B will be replaced with B bar. And as per De Morgan's law, complement of a product is equal to sum of individual complements, right? So A bar sum with B bar. Already we are having a complement, so one more complement, right? If A bar is X, B bar is Y, it is nothing but X dot Y whole complement, that is equal to X bar plus Y bar, right? X bar is nothing but A complement here, right? So A complement the whole bar again plus Y is a B complement the whole bar, correct? So what happens if you are complementing twice, right? Let us say 0 is there. We have complemented it. We got a 1. Complement of 0 is 1. We have complemented 1 again. How much will get? 0 will get. Okay. Similarly, if we are having a 1, complemented became 0. Again, we are complementing the same. Then we'll get the original 1, right? So if you are taking the complement of a variable or complement 2 times, this variable will be same as A and B. right? A double bar is A, B double bar is B, right? So A or B, and that is my OR gate. Correct. Correct. So bubbled NAND is equivalent to OR. So let me have a second question, the same slide. Second question, question number 2. Bubbled, bubbled NOR gate is equivalent to bubbled NOR gate is equivalent to same options, right? Very good. Which gate? Bubbled NOR is equivalent to AND gate, correct? NOR is nothing but A plus B, the whole complement. We said bubbled NOR, bubbled means inputs are complemented. So that's equal to A double bar dot with a B double bar, right? So complement of a sum equal to product of their individual complements, right? So A double bar dot B double bar, that is nothing but A dot B. That is my AND gate, correct? Very good. Right, Pujari asking one more doubt. Sir, is bubbled not is a buffer gate? Right, you are absolutely right. A bubbled not implies two NOT gates in a series. Okay, one NOT gate, another actual NOT gate. So this is corresponding to bubble. Okay, bubble. This is actual NOT gate. Right, if you're applying X here, okay, you'll get X complement here. Output will get complement of X complement. So X double bar, that is X itself. So you are getting same input as output. So it is equivalent to a buffer gate. Okay, correct. Bubbled node is a buffer gate. Correct. So shall I move to next question? Question number 3. Only if you are responding, only Venkata Krishna Chedan responding. Right, but duality is not right. Dual gate of not is not itself. And I didn't say anything about bubbling and dual. These two are independent process. Where you are relating bubble and dual, they are entirely different. Dual gate of not is not itself, and bubbling does not have any connection with the duality. Correct, Pujari? Okay, right. So I'm moving to third question. Question number 3. Right here, I'm having my XOR gate, XOR gate, right, with A, B, and Y. Okay, I am bubbling it, and that is equivalent to which gate? You'll have 4 options: OR gate, NOR gate, XNOR gate, XOR gate. Bubbling XOR gate, right? Right. The expression of XOR was Y equal to, what was expression? Different input will give me the output equal to one condition, right? So different means A0, so A bar, B1, so B. Second possibility is A1, B is 0. And here A and B are actual inputs, right? Actual input. So I'm not writing A and B because A and B have used here, so that will be confusing. So if this is an XOR gate with, let us say, P and Q, output Y will be P0 Q1 P bar Q plus P1 Q0 P Q bar, right? Here actually actual input is called P, right? Actual input is P here, no bubble, okay? But here actual inputs are A bar and B bar because of this bubble. right? So y will be equal to, right, p bar will be nothing but a bar the whole bar, because p is equal to a complement. Right? P is the actual input. Actual input is after the bubble, because I have a bubble here, right? So a bar equal to p dot with a q. What is q? Q is nothing but b complement plus p dot q bar. What is p? P is nothing but a complement. What is q? Q is b complement, right? B complement. So a double bar is nothing but a itself, right? B bar, a bar dot b double bar is b itself. So this is of the form XOR gate, right? A B bar plus A bar B is same as XOR operation. So if your XOR gates, both inputs are bubbled, or if you are placing two inverters at A and B, then the gate will be same gate, not change, right? Right. And based on duality principle, we understood that if a statement is valid, then its dual statement is also valid, right? What is the statement here? Now we conclude that bubbled XOR gate is same as XOR gate without bubble, correct? Right? A, B, A, B. Right? Then we are taking the dual. What is the dual of A? A itself. Dual of B? B itself. What is the dual of bubble? Bubble means not gate. Dual of not is not itself. Right? And that is same as dual of A is A, dual of B is B. Right? What is the dual of XOR? XOR is XNOR, correct? So I should take XNOR here because I am taking dual of this logic, XNOR. And I'm taking dual of this logic. Dual of XOR is nothing but XNOR, right? XOR is A XOR B, and its dual is OR sign with AND sign, that is called XNOR, correct? XNOR, and this is XOR, correct? So if you are bubbling both inputs of an XNOR gate, then the gate will be same as XNOR, no change. Right? Please remember this. In the case of XNOR and XOR, if you're bubbling both of its inputs, the property will be same as XOR and XNOR. Doesn't matter. Right? Clear? Okay. I think you have copied this. Shall I move to next question? Then copied. Only Ramya, Chetana, Sanish are responding. Okay. None of other students are responding. Copied. Then shall I move to next question? Clear? Right. Okay. So question number 4. In question number 4, I'm taking my XOR gate, okay, and cleverly I'm placing a bubble at upper input only, and this is equivalent to, you will have 4 options, 4 different options: XOR, XNOR, or NOR. What is your answer? It's all about the basic operation of XOR gate. If these are X and Y, XOR gate will produce output equal to X Y bar or X bar Y plus X Y bar, X bar Y, or with X Y bar, right? Here Y equal to B, right? Y and B are same, no bubble, right? And X equal to a complement, correct? So X equal to a complement, a bar, we have another complement. This is my X, that is a bar. What is Y? Y is same as B, not change. Plus, what is X? X is a complement. What is Y? Y is same as B and a complement. because I have a complement. So a double bar is a itself dot b plus a bar dot b bar. What is this? A dot b plus a bar b bar. A dot b will be equal to 1 if a equal to 1, b equal to 1. A bar dot b bar will be 1 if a equal to 0, b equal to 0. So 0, 0 and 1, 1, it will give me output equal to 1. Which logic gate it is? Same inputs, output equal to 1. Which logic it is? X NOR gate, correct? 0, 0, 1, 1, 1, 1, right? That is a property of X or X NOR gate. X NOR to triple 0, 0, 1, 1, 1, 1, both 0, 1 and 1, 0. Output will be 0. So that is nothing but option B, X NOR gate, right? Or is wrong. It's a X NOR. Okay. So that is very easy to remember. If your XNOR gate is complemented, one of the input is complemented, either upper or lower, doesn't matter, right? If one input is bubbled, it acts as complement of XOR, that is XNOR. Okay, XNOR. That is true if I am bubbling the lower input also. Doesn't matter. If I'm placing a bubble here, that is also equivalent to XNOR. Correct? But if I am bubbling both inputs, not change, right? And the same thing can be expanded to in the case of XNOR also, right? If I am bubbling one input of my XNOR, one input I am bubbling, it acts as XOR, correct? Complement of XOR, right? So that can be upper input or lower input, doesn't matter. If any one input is bubbled, it acts as the complement of that gate, right? If the input of XOR is bubbled, one input is bubbled, it acts as XNOR. If the input of any one input of XNOR is bubbled, it acts as XOR gate, complement of that, right? And definitely you can expect a question from this XOR and XNOR, right? XNOR and XOR. Both inputs bubbled, no change at all. One input bubbled, it acts as other gate, right? One input of XNOR is bubbled, it acts as other gate, that is XOR. One input of XOR is bubbled, it acts as another gate, that is XNOR, complement of that, XNOR, right? Is that clear? These identities are clear, right? Please respond. Clear?
Sir, repeat for last one, sir.
Yeah, I will repeat for XNOR, right? No problem, I will repeat. Any other queries? Okay, all right. One of your friend asked me to repeat the last case, that is bubbling of XNOR. No problem, let me repeat. One NOT gate is connected here like this for XNOR A, B. Okay. If actual inputs are X and Y, this will be X bar Y bar plus XY. Correct? XNOR operation 0, 0, 1, 1. Correct? Actual inputs. So very simple. Here X is nothing but A. Okay. So this will become A complement. What is Y? Y is nothing but B complement. Right. So B complement is Y. Y complement, one more complement plus what is X? A itself. Right. What is Y? B is not Y is nothing but B complement. So this is nothing but A bar dot B double bar will be B itself. If you are complementing twice, you will get the same variable, right? Plus A B bar. What is this? Which expression is this? A bar B implies A0 B1. A B bar implies A1 B0. So different inputs, I'm getting a 1. So that is equivalent to which gate? X or gate with A and B. Is that clear?
Yes, sir.
Okay. Thank you, Kamal. Right. So let us move to next slide. Question number 6. Question number 6, I will draw a little bit complex diagram, gate diagram. But you don't worry, you apply what you have learned, then identify the options. Okay. So I have one XOR gate, right? One input is 1, another input is X. Okay. Don't worry. And you should identify the value of Y. And you are given with 4 options, right? 4 options. 0, 1, X, X complement. The gate is an XOR gate, 2 input XOR. One input is logic 1, another input is X. X is a binary variable. X can take 2 values, logic 0 or logic 1. So it's very, very, very simple. It's all about the truth table of XOR gate, right? A, B are the input. Let us say A, B are the input. A is same as logic 1, right? B is nothing but X, okay? B equal to X, right? X is a binary variable. So X can take 2 different values, either 0 or a 1. 2 options are there, okay? But A value will be always 1 because A is connected to upper input is permanently connected to logic 1. Lower input can take either 0 or 1 depending on the value of X. So these are the possibilities. And I'm looking for output Y. What about Y? Is an XOR gate. If inputs are different, 1 and 0, I am expecting a 1. Okay. Inputs are different, output will be 1. Right. A equal to 1. If X equal to 0, X equal to 0, then I'm getting Y equal to 1. If X equal to 1, it will become 1, 1. Okay. If X equal to 1, 1, 1. Same inputs, property of X or is output will be 0 if inputs are same. Right. 0. Right. So what is the relation between X and Y? If X equal to 0, Y is 1. If X equal to 1, Y equal to 0. Right. So Y is nothing but complement of X, correct? X bar. If X equal to 0, I got Y is equal to 1. If X equal to 1, I got Y equal to 0. So that is nothing but Y equal to X complement. And that is my option T. Right. All of you answered D. Very good. If I'm slightly modifying my question with 0 and X with X nor, what will be your answer for Y? Same options. What is Y? Right. I think, okay. Right. Okay. Very good. Chedana saying that same T. Very good. Harikrishnan, we also said option D. Right. Very good. Randy Roy is also option D. Right. Very good. No problem. It's a truth table of X nor. You should not forget the truth table of X nor. What was the truth table of X nor? If I'm having two inputs, let us say A and B, A and B, Y. Okay. And A input is always 0, right? A is 0, A is 0. B is connected to X. X can take two value. B is nothing but X. So X can be either 0 or a 1, right? It's an XNOR gate. If X equal to 0, both inputs will become 0 and 0. XNOR gate, Y will be 1. Second case, if X equal to 1, A0 X1 implies A0 B1, right? So they are different, 0 and a 1. XNOR gate, if inputs are different, XNOR gate will give me a 0. That is the property of XNOR. different input 0, same inputs 1. Whereas XOR gate, same input 0, different inputs 1. In the case of XOR, here it is XNOR, right? So same inputs 1, different inputs 0, right? So this column was equal to X. What is the relation between X and Y? X and Y. Y is nothing but X equal to 0, Y 1. So X complement. X equal to 1, Y 0, and X complement. So same answer, right? Right. And that is obvious. Look at your initial problem. Output, you got it as X complement, correct? And what is the change in question? Question changed 1 to logic 0. That is a dual of 1 is 0, right? Dual of X is X itself. Dual of X or is X nor. So output also will be its dual. What is the dual of X complement? X complement itself, right? So directly you can go for X complement, or this way you can prove it as X complement. Okay, this is clear. Then everybody got X complement. Any doubts, any queries? Should I repeat? Please respond. Clear? Yes or no? Okay, let us move to question number 7. And this is a very simple question. We are having AND gate with one input logic 1, another input is X. What is Y? What is Y? Look at the question and tell me the answer. You need not write. What is Y? AND gate product of 1 and X, that is nothing but 1 dot X, that's equal to X itself, right? Same question with NAND gate X and 1. What is your answer? Y equal to NAND gate. It is X dot 1, the whole complement, correct? X dot 1 whole complement. That's equal to X complement, right? Very simple. You need not copy the questions, okay? Very simple. Directly look at the question and tell me the answer. And I have another one for NOR gate. Upper input is 1, lower input is X. What about Y? NOR gate, NOR gate. Upper input is 1, lower input is X. What is Y? It is a NOR gate, NOR. You should recall the property of a NOR gate. What was the property of a NOR gate? A, B, Y, 0, 0, 0, 1, 1, 0, 1, 1. What is the property of a NOR gate? NOR gate will produce logic 1 if and only if both of its inputs are zeros. Correct? This was a suitable, right? So if any one input is 1, any one input is 1, output will be what? 0. Directly you can write it as 0. Or you can write the expression also. What is the expression? 1 or with X, the whole complement. 1 plus a variable is always 1, right? Whole complement, that will be 0. Okay, 0. Correct? Okay, okay, correct. Question number 8. Okay, I'm having a small diagram of logic gates in which I'm having AND gate first. Inputs are connected together. I will connect A. Okay. Similarly, I'll have another two input AND gate. Inputs are connected together. I will call it as B. And the individual outputs are connected to third AND gate. Sorry, third AND gate. And have a function f that will be a function of inputs A and B. You should identify that function. 4 options. and, or, nor, NAND. NAND. All are AND gates. Right? Very good. Harish and said option A, and very good. Sanesh, Pooja, right? Very good. So it acts as a buffer. A will appear here, B will appear here. So this is nothing but A and B, that is AND gate. Okay. What happens if I'm inserting a bubble here? Please look at the question and tell me. First two gates were initially AND. Now I replaced them with NAND gate by placing a bubble at the output. It's very simple. A dot A whole complement, A complement. B dot B the whole complement, B complement. Right? Very simple. Right? And this will be product of what? A complement here, B complement here. So this is product of A complement and B complement because the last gate is AND gate. Correct? So what is A bar dot B bar? Product of individual complements is equal to what? Sum of their complement. Correct? Complement of a sum equal to product of their individual complements as per De Morgan's law that we have learned in the last class. So what is this? It's a NOR gate. Correct? NOR gate. Okay. Shall I move to next question? Question number 9. Right. Okay. Okay. Another technique in the chat was that bubbled and is equal to NOR. Correct. That is also right. What he was trying to say is the last was and, right? This is a NOT gate actually. So I can replace that with a bubble, right? Right. Or I can replace that gate with a NOT gate. Shorted NAND is act as a NOT. Similarly here also, right? So this is nothing but bubbled and bubbled and is same as NOR that we have learned earlier. Yes, that is also correct. Right. Okay. Question number 9. Okay. Let's have another small network of logic gates. Right. This is my NOR gate A, B. This is also a NOR gate, right? Followed by another NOR gate. This is equivalent to which gate? NOR gate itself, OR gate, AND gate, AND gate. 4 options. Please provide your answers. Right, very good. NOR gate with inputs shorted act as NOT gate. So A complement will be the output. B complement will be the output. This is nothing but a complement or with B complement. It's a NOR gate. So all complement, right? Complement of a sum is equal to product of their individual complements. That is nothing but A dot B. That is your AND gate. Or you can replace the circuit with you can redraw the circuit with the bubbles here. Okay. NOR with the together input is bubble, not. So AB bubbled NOR is equivalent to AND gate. That is also true. Right? Correct? So I think you will be able to answer these kind of questions that is going to appear in the examination. Right? And let me complete another topic also. Then we'll go to previous questions. Right. So let me complete the topic universal gates. Okay. Universal logic gates. Universal logic gates. Right. We are having two logic gates, namely NAND and NOR. They are called NAND and NOR are called universal gates. Okay. And the same question appeared so many times in the examination. Okay. Which of the following is a universal gate? Right. So please note that only two gates are universal gates. They are NAND and NOR. Right. They are calling as a universal gates because all gates, all gates can be implemented using either NOR gates only or NAND gates only, right? If you would like to implement an AND gate, you can make use of only NAND, or you can make use of only NOR. If you would like to implement XOR or XNOR gates, similarly, you can implement the same by using only NOR gates or only NAND gates. Or the other way, these two gates are sufficient enough to implement all other logic gates in Boolean algebra, right? Okay, clear? So please understand that universal gates are NOR and NAND. Okay, that is very simple. Okay, so let us move to previous questions. And one more topic we left out. One of you asked me last class that three input case. Okay, three input. That also let us discuss. Three or multiple input logic gates. Okay, so three input and right. Let us say A, B, C. Right. So three inputs A, B, C. That implies 8 combinations are possible. Right. Triple one. Okay, it's an AND gate. It's a product. So very simple. Product or AND operation between the inputs, right? It is clear that if one input is at logic 0, definitely output will be 0 for my AND gate, right? The only one condition at which multiple input AND gate will give me a logic 1 is all one condition at the input or triple one condition at the input. Very simple, similar to two input gate. Similarly, NAND gate, NAND gate, NAND gate, just opposite to this AND. Okay, right? So 1, 1, 1, 1, 1, 1, 1, 0. So multiple input or three input NAND gate will give me always a 1 if at least one input or more than one inputs are at logic 0, and it will produce a logic 0 if and only if all of its inputs are 1, similar to two input case. And multiple input OR is also very simple. Multiple input OR gate. What is the property of OR gate? OR gate is very simple. OR gate will give me an output 0 condition if all of its inputs are zeros. All other cases output will be 1. Very simple. This is for 3 input OR. Right. And 3 input NOR will be just opposite to this. Right. 1 all zeros. 3 input NOR. Right. 3 input NOR will give me a logic 1 if and only if all of its inputs are at logic 0. Right. Okay. And the definition for three input XOR and XNOR gates are slightly different. Okay, I didn't think of teaching three input XOR or XNOR gates in the class, but yesterday one of you asked me the query, right? So three input XOR gate or multiple input XOR gate. Inputs can be any number, right? One, two, etc., etc., any number, right? So let us take 3-bit example, X, Y, Z. 3-bit case, all of you knows that how many combinations are possible? 8 combinations, 2 power 3, 8. Okay, like this, 8 combinations are possible. Okay, 8 combinations are possible. And the property of multiple input or 3 input or 2 input, any XOR gate with any number of input is that, please listen carefully, this is important, please don't confuse. XOR gate will produce output equal to 1 if and only if, please listen carefully, if and only if number of ones are odd at the input side. Number of ones are odd. Okay, right? Number of ones are odd. Okay, so first combination triple zero, number of ones equal to 0. 0 is an even number, so this is 0. Next one is 0, 0, 1. Number of ones is equal to 1. 1 is an odd number. So 1. 1 is odd 1. 0, 1, 1. We have even number of ones at the input. So it is 0. 1, double 0, odd number of ones. 1, 0, 1, even numbers. 1, 1, 0, even numbers. Triple 1, odd numbers. So this is the truth table corresponding to 3 input XOR. And the definition, output equal to 1 if and only if number of ones are odd is valid for an XOR gate with 2, 3, 4, 5, 6, 7, etc. any number of inputs, right? And that is valid for 2-bit case also, 2-input case also, right? This was the truth table of 2-input XOR gate, A XOR B, right? What was the definition? Odd number of ones will give me 1, right? Even number of ones, odd number, even number. So that was the truth table, right? Whereas my multiple input XNOR will give me a logic one if and only if number of ones are even. Number of ones are even. This is for odd, right? So 0 number of one, 0 is an even number, right? This is for XNOR. XNOR 0, 0, 1 odd, 0, 1, 0 odd, 0, 1, 1 even, 1, double 0 odd, 1, 0, 1 even, 1, 1, 0 even, triple 1 odd. So this is a truth table for multiple input or 3 input XOR and XNOR gate. Okay, is that clear? Right, right, very good. Odd number of one detector and even number of one detector. That is correct. So unlike other logic gates, a special property of XOR and XNOR is that odd number of ones and even number of ones. Okay, odd number of ones XOR will give you 1, even number of ones XNOR will give you logic 1. Right, is that clear? Right, for triple zero case. Okay, a definition is for XOR, this case XOR, odd number of ones should be there at the input. Right, look at triple zero case. 0, 0, 0. Number of ones are 0. Number of ones are 0. Right, and 0 is an even number. Right, number of ones should be odd in the case of XOR to produce output equal to 1 condition. Right, so triple zero implies no logic ones, 0 logic ones. So 0 will treat it as an even number. So output will be 0. Whereas in your XNOR case, number of ones should be even. Number of ones at input side should be even. Here, number of ones at input side should be odd. Right? Right? So triple zero case 0, 0, 0. In the case of XNOR, the definition is number of ones should be even to produce 1 at the output. triple zero, number of ones are zero. Zero is an even number, so I am having output equal to 1 in the case of XNOR gate. Right? Is that clear, Gaurav? Right. Thank you. So let us move on to the question. The type of logic circuit is represented by the figure shown below, 4 options. So it may not be clear, so I will try it. This is an inverter. Okay, this is also an inverter, right? This is AND gate. Okay, this is also AND gate. This one is OR gate. ABCD 4 options. Please provide your answers. A, B. Right, option B, correct? So we'll have a complement here, A bar and B bar, correct? Here A and B, right? It is an AND gate, so we'll have A bar, B bar here, very good. This is AND AB. So this is an OR gate. What is the property of OR? It will OR between its input, right? Upper input is A bar, B bar, or with lower input is AB. This stands for which gate? X NOR gate, right? Very good. So option B is correct. Correct. Okay, copied. Done. Right. The next question is A bar dot B bar dot C bar equal to D represents A. First option NOR gate, XOR gate, NAND gate, AND gate. Okay. A bar dot B bar dot C bar equal to D represents which gate? Right. Different answers. Chedana says NAND. Sanesh Noor. Harikrishnan. Mrutula. Chetana, right. Which one it is? Look at the expression. It's a product of complements, right? As per De Morgan's law, what is equivalent to the product of complements? Complement of a sum, correct? Is equivalent to the product of their individual complements, correct? So which gate is this? A or B or C, the whole complement, say NOR gate. 3 input, NOR gate, correct? 3 input, NOR gate. VK answering NAND. NAND is wrong. Okay. NAND is wrong. It's actually bubbled and correct. Bubbled and 1, 2, 3. A, B, C. Right. Bubbled and. Bubbled and is equivalent to NOR gate. NOR gate. Okay. So NAND is wrong. NOR gate is the right choice. Correct? Clear? Copied? Any doubts? Any queries? Shall I move to next question? Only Chetana, Gaurav, Venkata are responding through the chat box. What about others? Any difficulties? Any problems? Please respond. If it is clear, please type a Y in the chat box so that I can move to next question. Right. I think it is clear. Right. Let us move to next question. Right. NAND gate is called a universal gate because 4 options. It is most commonly used. All logical functions can be realized by using NAND gates alone. Third option, all minimization techniques can be applied to it. Fourth option, it can realize and not functions. NAND is called universal gate because it can realize and not functions. No. I have options B in the chat box. Only one person got option D, right? And right option is second option, option B. Okay. All logical functions can be realized by use of NAND gates. Let me explain that also. Right. So our minterm expression, SOP expressions are sum of individual product terms. Correct. Individual product and their sum. Right. Please listen. Individual products can be implemented by AND gates. Correct. Right. All functions that is represented in sum of individual product form, SOP form, are like this: individual products and a sum in between. Okay. So using AND gate, you can easily implement that product, and using OR gate, you can easily implement that sum. So to implement an SOP function, SOP expression, we require and OR gates. Sometimes in the variables, you may have a complement also, right? Complement also may come. So to implement that complement operation, we require which gate? NOT gate, right? Not and OR gates are more than enough to implement any Boolean function, because all Boolean functions can be written in this form, SOP form. Okay. So how to implement AND gate using NAND gates only? If we are using our NAND operation twice, right? A, B, I will get AB complement here. Again, not operation, I will get AB here. So that is equivalent to NAND. That is equivalent to AND, sorry. So the AND operation can be implemented using NAND gates only. So you require only NAND gates to implement AND operation. Right. What about OR operation? How to implement OR operation? A bar dot B bar. The whole complement is nothing but A or B, correct? A or B, correct? A double bar plus B double bar as per De Morgan's law. So a complement can be implemented like this using one NAND gate. Similarly, B complement can be implemented like this using another NAND gate. Okay, NAND gate. So if I'm taking the product of these two again using NAND gate, I will get what? A complement dot B complement, the whole complement. That is same as this, same as NOR, same as OR, sorry, same as OR, right? To get a NOR, I have to use another NOT operation. How to use NOT operation? If you are giving A or B here, you will get A or B complement here, right? Inputs shorted together, right? So OR operation, NOT operation, and operations, all these operations can be implemented using NAND gates. So all Boolean functions can be implemented using NAND gates. So that's why NAND gates are called universal gates, right? And the statement was all Boolean functions can be implemented using which gate? NAND gate. Okay. What is the dual statement? If that statement is true, initial statement is true, the dual statement is also true. What is the dual statement? The first statement was all Boolean functions can be implemented using NAND gates. What is the dual statement? All Boolean functions can be implemented by using, what is the dual of NAND? NOR gates, correct? Dual of NAND is NOR. Dual of NAND is NOR. Okay. So if we can implement all Boolean functions using a NAND gates only, the statement is true for its dual gate also, right? So NOR gates can be used to implement all Boolean functions, or the other way, all Boolean functions can be implemented using NOR gates only. Similarly, all Boolean functions can be implemented using NAND gates only. So that is why NOR and NAND, they are dual to each other. Okay, NOR and NAND are called universal gates. Is that clear? And the statement, it can be realized. It can realize A and NOT functions are true, but that is not the correct answer for the given question. Okay, that statement is true. It can realize and NOT functions that we have proved here. Okay, not and. Clear? So please don't forget, universal gates are NAND and no, sorry, right, NAND and NOR gates. Why they are universal gates? All Boolean functions can be implemented, or all Boolean gates can be implemented. XOR, XNOR, NOR, NAND, or any function, any logic gates can be implemented using only AND or only NOR gates, or using both. Right? Is that clear? Shall I move to next question? So second option is the right answer. Okay, I'm moving to next question. The simplified form of Boolean expression A plus B bar plus A bar B dot with C. Let me write it. A or with B complement or with A complement dot B dot with C. Four options. Okay, again I'm having different options, C and D. Right. Right. The problem is very simple. The theorems that we have learned in the last class is more than enough to solve this quickly. Right. So I'm writing A plus A bar dot B second plus B complement dot with C. What is A plus A bar B? What I learned A plus A bar B? A plus A bar B is nothing but A plus B complement dot with C. What is B plus B bar, A plus A bar, or X plus A bar always equal to 1, right? So A plus 1, okay, because B plus B bar is 1. What is A plus 1? A plus 1 is always 1, X plus 1 is always 1. Any Boolean variable plus logic 1 is 1 always, right? So 1 dot C, that is nothing but C itself, right? So option C is the right choice, correct? Okay, I'm moving to next question. Which of the following Boolean algebra rules is correct? Which of the following Boolean algebra rules is correct? Okay, so let me rewrite the options. A dot A equal to 1. Second option, A plus A complement B equal to A or B. Third option, A plus AB equal to A plus B. Last option, A or A dot with A or B equal to B. Which one is correct? A complement can be represented either this or like this, both ways. Okay. So it's a multiple choice question. Only one option will be true. So if A plus A bar B equal to A plus B is observed, then you can tick the second option. You need not check the other options because for a given question, only one option will be true. And we understood that the second option is true. A plus A bar B equal to A plus B. Correct? So you need not check other options. So B is the right choice. Correct? Copied? Then shall I move to next one? Right. The following waveform is a pattern for which logic gates. So waveforms are given. I will redraw the waveform for better readability. Right. Two waveforms are given A and B, that is applied to the logic gate. Then output is also shown. Okay, output is also shown. This is first input. This is my second input. Right. Okay, and output is shown X. Right. Right. So look at the waveform. This is my output X. Okay, A, B are the inputs. Right. Here, small interval of time, output is 1. So B equal to 1, A equal to 0 in that interval. Right. In this interval, output is equal to 0 because this is 1, this is also 1. Right. Then again, this is 0, this is 1. So my output is equal to 1. Output is equal to 1. So by observing these three sessions, you can easily identify which gate is this. 0, 1, output is 1, 1, 1, output is 0, 0, 1, again output is 1. Right? If inputs are different, 0, 1 and 0, 1, output equal to 1 and 1. If inputs are same, output is equal to 0. Which gate it is? It is an XOR gate. Right? So instead of truth table, they have given you the waveforms of inputs and output. Right? It's very simple. So don't be upset while observing a waveform in the question. Right? Just look at the waveforms, try to identify the logic gates. Okay, is that clear? Any doubts? Then clear, copied. Then we'll move to next question. Then okay. Okay, the Boolean expression, a complement plus B dot with A plus C complement dot with B complement plus C complement simplifies to I have four options. Answers. Right. Very good. Option C. We can easily simplify this. This is of the form A plus B dot with A plus C. So that is A plus BC. A is nothing but C complement. B is A, C is B complement. Right. A bar plus B dot. Okay. Then you can easily simplify that. A dot B bar into A bar plus B. Second term is C bar into A bar plus C. A bar plus B. This term will be always 0. So we'll get A bar plus B dot C bar. And that is my third option. Right, right. What Chedana told is also correct. Last two terms we could simplify as C bar plus A B bar. That is also right. Correct. So anyways, you can simplify it quickly. Right. And there is a trick here also. That is in your given expression, C complement, B complement, and A complements are there. Right. You cannot avoid, you cannot remove all complements. So at least one or two complements should be there, and that also satisfies our option C. Okay. That's up to you. You can follow any method. Okay. Copied it then. Copied. Shall I move to next one? We are having 10 more minutes. Okay. Oh, this is a direct question. Dash and dash gates are universal building block that we have discussed right now. Which are those gates? NAND and NOR are universal building blocks. Okay. A option is the right choice. That was a straight question. Right. Next question is an XOR gate has inputs A and B and output Y. Then the output equation is. That is also direct. XOR gate is there. Inputs are A and B. Okay. A and B. What is the output expression? That is A bar B plus, sorry, A bar B plus A B bar. Correct? A B bar. So that is my option C. Correct. That was also a direct question. Okay. Right. Again, the question is repeating which of these are universal gates? Both NOR and NAND gates are universal. That is also true. That is also straight question. Right. Next question is which one of the following Boolean expressions are true? Four options are there. Equality sign is missing here. Okay. Which of the following Boolean expression is true? A plus B dot A plus C equal to AC plus BC. A plus B dot A plus C equal to AB plus C. A plus B dot A plus C equal to A plus BC. Fourth option, A plus B dot A plus C equal to AC plus B. Which options are correct? This is also true. Direct question. Straight question. We have learned that A plus B dot with A plus C is equal to first variable A plus the product of the other two variables C, B and C. Correct? That is also true, right, straight question. Okay, then that is also simple. Correct. Right. Next one is simplified form of the Boolean expression. Simplified form of the Boolean expression. A plus B plus AB dot with A plus C. Four options. Answers. Right. Very good. This A is common here. A is common here. So I can take A common 1 plus B plus B. Okay. Taking A common dot with A plus C. 1 plus B, everybody knows that it will be equal to 1. So 1 dot A will be A itself. So A plus B dot A plus C form. That is why I said this expression is important. Distributive law, A plus B dot A plus C equal to A plus BC. Correct? A plus BC. And that is in our option C, A plus BC. Correct? Correct. So please don't forget this. A plus B dot A plus C is always equal to A plus BC. First variable plus the product of other two variables, B dot C. Done? Copied? Okay. Right. And this is a question that we didn't discuss actually. Okay. An AND gate may be visualized as switches connected in series, switches connected in parallel, most transistors connected in series, none of the above. AND gate. Right. Right. Logic 1 means the switch is closed. This is my input and this is my output. Right. So logic 1 means switch is closed. Logic 0 means switch is open. Okay. So AND gate implies both inputs should be equal to 1. That implies it acts as a series switch. Switches connected in series. Whereas your OR gate will be acting like switches connected in parallel. Switches connected in parallel like this. This is for OR gate. Okay, so that is also trivial question. You can answer using your common sense. So AND operation is a series product operation. Both should be one. Both switches should be closed. Right. OR operation is either A or B, A plus B. Either first switch or second switch can be closed so that there will be a path from input to output, either upward or downward, or using both switches together, one case. Right. If both are open, there is no path between input and output. Both open means 0 0 condition, 0 0 condition, output will be 0. That is for an OR gate. So parallel switches or series switches for your AND gate. Okay. And we have one question from duality theorem. The dual of Boolean theorem A dot B or C. Okay. A dot B or C, and there is an equality sign here that is missed. Equality sign equal to A dot B plus A dot C is the dual form of the dual of Boolean theorem. A dot B or C equal to AB plus AC is. What is the dual form? How to take the dual that we have discussed so many times? A or with the B dot C equal to A or B dot with the A or C. And that is my option C. Correct. Option C. Right? It's straight direct question. Hardly it will take 2 seconds to answer. Right? Okay. Clear? Right. That is also next question is also direct question. NAND gate is equal to right. NOR gate with negated input. NOR gate with negated input. AND gate with negated input. None of the above. What do you mean by negated input? Negated input. Right. Negated means bubbled. So which one is correct? NAND gate is bubbled. NAND gate is equivalent to which gate? No, option C is wrong. No. NAND gate is equivalent to which one? NAND gate was equivalent to which gate? NAND is equivalent to which gate? Negated or correct? A, B, A, B. You'll have A, B the whole bar. That's equal to A bar plus B bar. You'll have A bar plus B bar. Right? So there is an error in the options. You can make it as OR gate with a negated input. Okay. OR gate with negated input. Right. Bubbled OR. Correct. Then second part, NOR gate is equivalent to which one? NOR gate is equivalent to right. Very good. Chetan is saying right answer. NOR is bubbled and right. So you can make it as option C as AND gate with a negated input. Bubbled AND is NOR. Correct. Okay, none of the above is there. Okay, no problem. But I think there is a printing mistake in the question. Okay, if you are observing the same question, you can go for none of the above. No problem. So let us take both cases, none of the above. Right, no problem. This is or with the negated input. This is and with the negated input. Right, because Gaurav answered option D. So and that is also right, no problem. So you can either take option D or you can correct option C, then go for option C. Both ways it is correct. Clear? Done? Right. Next question is sum of products can easily be represented by sum of individual product, sum of products, sum of individual products can easily be represented by OR gate feeding to AND gates feeding to OR gate, NAND gate feeding to OR gate feeding to NAND gate. So individual product then sum, correct? So individual products will be AND. So we'll have three different AND, right? AND will give me the product terms, okay? That I'll feed to OR gate, okay? For this OR gate. So AND gate feeding to OR gate. AND gates are feeding the OR gate. Correct? AND gates are feeding the OR gate. So second option is correct. Clear? Okay. No worries. Very simple. And this is my last question. So let us wind up after this. The circuit shown in the figure is functionally equivalent to. So let me redraw the circuit for better readability. This is NAND. Second gate is also NAND. This is A. This is B. This is A. NAND. This is B. NAND. It is connected to NAND again. Okay. Four options: NOR, OR, XOR, NAND. A, B, C, D. So we'll get A bar here. I will get B here. So A bar dot B, the whole complement here because it's a NAND gate. I will get A here, B bar here. I will get A dot B bar, the whole complement here. This is my output. Output is also NAND operation between two inputs. Inputs are A bar dot B, the whole complement, dot with A, B complement, the whole complement, again, the whole complement, right? So these are individual terms, right? Complement of a product is equal to sum of their individual complements. So A bar dot B, the whole bar, plus A, B bar, the whole bar, the whole bar. Double bar will become, will cancel each other. Double bars will cancel each other. Okay. X double bar will be X itself. So A bar dot B double bar is A bar B itself. Okay. Plus A B bar double bar will be A B bar itself. So this is nothing but A bar B plus A B bar. That is my XOR. That is my XOR gate. Right. Look at this. We have implemented an XOR gate using NAND gates only. Okay. XOR gate using NAND gates only. So all gates can be implemented using NAND gates. Okay. So C is the right choice. Clear? So let us wind up. That's all about Boolean algebra and logic gates. Okay. Everything we have discussed. Okay. So if you don't have any queries, let us wind up. Thank you all. Thank you for listening the class. Thank you for your patience. Bye bye. We'll meet next time.